It's all memorization and spatial reasoning. I can make you like be the molecule, you can think about where those lone pairs are, think about the shape you take on, but I can't put my brain in your brain. Can't do that switcheroo thing. So VESPER, that's the little acronym that I used for giving you guys the skills to, or the steps to draw structures. Remember we did like the V, count those electrons, M, skeletons, blah, blah, blah. So VESPER is actually not just an acronym for our little steps for drawing structures. It actually is a theory that we work through to then give names to our structures, geometries. So valence shell electron pair repulsion theory. So what is the valence shell doing with other electrons? Repelling, right? Duh, we knew electrons repelled anyway. But since they repel, and that causes some atoms to change their arrangement in space, we achieve new geometries. Those are molecular geometries that we're looking at. And those are the tetrahedral and trigonal pyramidal and trigonal bipyramidal and seesaw and T-shape. So basically this theory is what's deriving all those molecular geometries. So really I just wanted you to understand that we're talking about maximizing the distance between electrons, and that minimizes the repulsive force. And we like to bring pairs far, far, far away from each other and from bonded pairs because they take up more space than the bonded pairs. So we try to keep them on the equatorial or the axial plane. Which one? Most of the time it's going to be equatorial because the only time equatorial is a problem is when you have 4 on the equatorial plane, because 4 in the equatorial plane would mean what bond angle? 90, which is pretty repulsive. Sometimes we'll have 2 or 3 things on the equatorial plane, which sets lone pairs apart by like 120 or more, which is more beneficial for them. So basically lone pairs spread out, we put them far away. It makes a shape. We name the shape. Got it. Okay. So I'm going to show you this quick video on that, which might help some of you guys who are spatially challenged. Hold on. Let me just cut that off real fast. Every time. Okay.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge, and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron.
corresponding to look?
Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent, like your elbow would be bent. And chlorine trifluoride, or ClF3, is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't.
All right, that's really all you need to see there. And all right, so in terms of geometries, we've been naming so far molecular geometries. That is because the Vesper series speaks to how the atoms are arranged. So far we have just been naming molecular geometries. There's another geometry, which it's much easier than molecular. It's called electron pair geometry, where we call everything the same. We call out lone pairs and bonded pairs the same because we just call them effective pairs or electron domains. So if I ever say count electron domains, you're calling out lone pairs and bonded, actually, let me just call those ligands, a little easier. Ligands equally. So let's say you're looking at an atom and you count 2 lone pairs and 2 ligands, well, that's 4 total. That electron domain geometry or electron pair geometry would be called tetrahedral because there are 4 attachments. So basically they're equating all the attachments in the same way. So there are only 5 electron group geometries because there's only really 5 main ways that you can make a combination of attachments. So a linear structure would only have, so it's going to maybe like a central atom, and it's going to have 2 things attached to it. So things could be 1 lone pair and, a couple of lone pairs, 1 lone pair and then 1 ligand, or it could be 2 ligands. No matter what, as long as there's only 2 things, then we're going to call that out as 2 electron domains, and we will call that overall electron group geometry as linear. So then how many electron domains would a trigonal planar structure have? Say again? 3. So 3 electron domains. Doesn't matter if they're lone pairs or ligands, or double bonds or triple bonds. Those are all counted equally. That would be a trigonal planar structure. And then how many electron domains for tetra? 4 electron domains. Next, 5 electron domains and 6 electron domains. So if you're ever asked to identify the electron group geometry, count electron pairs or bonded pairs or doubles and triple bonds all the same way, count how many electron domains you have and assign the shape. So we care about really just where are the electrons. You did not learn that in honors chem. That's why this is just a little bit new. You learned some of these names, but you didn't learn they were called electron geometries or electron pair geometries. Now, with respect to these, all of these shapes repeat themselves in the molecular geometries, but we start to call the molecular geometries out a little bit more specifically because we're looking at how the atoms are shaped. So like the T shape, there are 4 atoms, 3 in a line, and 1 down, which then we call out as T-shaped, but really it's one of those above as well. Okay? So these are all the shapes that we've kind of mentioned so far with respect to molecular geometry. Octahedral is the same as what? So it's got 8 faces, right? Say again? Square bipyramidal. And I visualize those 2 pyramids better than thinking of it as octahedral, so if that helps you there. So, for example, seesaw has 4 atoms in its structure, like one of it, in terms of what is bonded to the central atom, and it has 1 unshared pair, aka lone pair. So overall, it has 4 plus 1, 5 electron domains. So though it's called seesaw in molecular geometry, what is it called in electron group geometry? Trigonal bipyramidal. If you have T-shaped, which is 3 atoms and 2 lone pairs, again we have 5 electron domains. What is it called in electron group geometry? See how electron geometry is a little simpler? They look at how electrons are arranged, not really atoms. Molecular geometry look at how atoms are arranged. Yeah. if you memorize this chart here. Yeah. Now it's a lot to memorize. I think it's easier to visualize, unless you're Cassie. Okay. So, and with respect to molecular geometry, is really what they're specifying, like why this is different, is they're actually looking at the repulsion, and they're looking to see how the atoms are arranged because of those lone pairs repelling. Okay. So the main difference is that repulsion is taken into account. So go ahead. Let's just draw chlorine trifluoride. Chlorine trifluoride. Draw that out from your post. And once you get it drawn, name the molecular geometry, electron group geometry, and bond angles as best you can with visualization. All right, visualizing this, what are you visualizing on the axial region? Christian, what's on the axial region? One fluorine on top, one fluorine on bottom. So you're thinking about, okay, so you're trying to get those ligands as far, or those ligands that were created there. I've drawn it like this, but it doesn't matter. You can think about it in another way. So you're thinking fluorine up top, fluorine down low. Where's the other fluorine? So on the equator, or the equatorial plane. Okay, so let's put one out. I'm just going to put it out to the left. All right, so that gives me a 90-degree angle here and here, which is okay. I haven't incorporated a lone pair, so where am I putting a lone pair? On the equatorial, I'm just going to bounce this one back into the board, and I'm going to put this one forward. Okay, so why is it valuable for, favorable for the lone pairs to be here? 120-degree angle between this fluorine and this lone pair and that back fluorine. So there's a 120-degree angle here. And then, yes, it's not great, but they do have 90 to the top and bottom fluorine, so the axial ones. So that's more beneficial for them. What is this shape in electron group geometry? Trigonal bipyramidal, because it's 1, 2, 3, 4, 5. 5 electron domains gives you trigonal bipyramidal. And you can actually see that pyramid and pyramid if you think about it. This is the middle with the triangle, and you have a pyramid on top and pyramid on bottom. And then in terms of molecular geometry, it's what? Say again? T-shape, yep. It is the molecular geometry. Okay. All right, let's look at polarity, and then we're going to go to our lab. Molecular polarity is a little different than bond polarity, but everything kind of plays together. So understanding the bond polarity plus the geometry and then visualizing where the electrons are placed is going to be how we determine a molecule's polarity. Read and write down what you want first. Some of this was in your reading, but So we've mentioned the keywords between polar and non-polar before. So remind me, when you hear polar, do you think equal or unequal? Unequal, right? So that unequal is referring to an unequal distribution of charge. We have a partial negative and partial positive end on a molecule. And then non-polar means, or what keyword comes into mind? Equal. So we have an equal distribution of electrons, or we have an equal pool of electrons left and right, so they cancel each other out, or top and bottom, they cancel each other out. So if the geometry allows for the cancellation of these dipoles, dipole moments, then what you overall can do is say, okay, they nullify each other, and therefore we have a nonpolar molecule. That's going to be more on the next slide. So this equation, not a really big important thing here, just understanding that when we reference dipole for molecules that are polar, we actually overall have a dipole moment that's established on the entire molecule, not just on a bond, but on the entire molecule. And we give it a unit of Debye's, okay? Debye units, which is a coulomb meter, because coulomb's referring to like charge and meters the distance. So that's how we're playing it into like the length of a charge distribution. And that's just the unit for it. We will never calculate with it, okay? Just know what Debye's are. And then I had, did I have some of my class read this last year? The polar bear and penguin. I just thought it was cute. So we have a situation where they're sharing an ice cream cone with a double scoop, 2 electrons in a bond, right? And the polar bear and the penguin are not sharing equally, so that creates a what kind of bond? A what kind of bond? Polar covalent bond, and so that creates this differential on where the charges are in the molecule, because in this case, this HCl, there's only one bond, H bond to Cl. So with that being just a singular bond, it makes not only the bond polar, but it also makes the molecule polar, because we have a partial negative and a partial positive caused by the bond and the geometry. So they both play into this. I'll show you these pictures in a second. Okay? And you can see here, we have hydrofluoric all the way to hydroiodic, and this red part's supposed to be representing, maybe you can tell me that. What's the red supposed to be representing? A what? Not just a negative charge, not a full negative charge, partial negative, because this is an ionic, right? So this is representing a partial negative, leaving us with a partial positive over here, versus, so that's HF, right? So F is super duper duper electronegative, and HI, you again still have a partial positive, but partial negative, but the electronegativity differences between these two and these two are vastly different. So we have a very, very polar molecule here, and this one's partially, like just very, very minorly, just partially positive and negative. So it is still polar, but one is more polar than the other. So we can actually have a continuum of polarity as well. Okay, so let's look down at, let me look at these first, okay? So we have water, right? Okay, why is water bad? Because the lone pairs do what? Repel, right? Vesper, valence electron pair repulsion. These electron pairs here, there are 2 little dots there if you can't see them. They're repelling these bonded pairs to give it from a linear drawing to a bent structure. So if these lone pairs are up here and they're not canceled out by a completely 180 opposite kind of a lone pair, you end up with a very partial negative on the molecule. And these hydrogens, you can actually see my 2 arrows pointing up. Why is it showing hydrogen pushing electrons towards oxygen in this bond? Well, it doesn't want to donate, because that would be like me thinking ionic, so we're transferring. So why are the electrons in this bond closer to oxygen? Oxygen's more electronegative. So this bond between O and H is just going to have its own little polar, it's polar covalent. So it has its own little dipole moment, which is what that little arrow means. So because this is more electronegative, it's pulling electrons towards itself. But they're still there, they're just not shared equally. There's 2 electrons, they're just kind of towards the oxygen. So since that's happening here and here, that leaves us with a lower electron density on the hydrogens, which leaves us with an overall partial positive charge. So would you say this is equal or unequal distribution of charge? Unequal, therefore it's polar. Same thing down here, which this is bent, so it was a little bit more complicated. With this is linear. Can't really mess this one up too much. You have an HF bond. Who's more electronegative? For sure. So we have a little dipole moment pointing towards fluorine. Well, that is now superimposed on the molecule because it's linear, so that just is going to be the same direction, leaving us with a partial positive on the little hash and a partial negative at the arrow. So we always point towards the more electronegative one. So overall, this molecule is also polar. Okay. So looking down at carbon tetrachloride, what's the shape? Tetrahedral, okay? And in this bond between carbon and chlorine, who's more electronegative? Who? Chlorine for sure, right? So you can see a little bit of a dipole moment on the carbon and chlorine bonds as well. So if carbon is allowing chlorine to have a greater share of electrons, we draw the dipole pointing towards chlorine, again and again. So that leaves us with carbon having a node of positivity around it, which we write a partial positive there, and each chlorine contains a node of partial negative around it. So would you say this is an equal or unequal distribution of charge? Say again? It's actually equal, because if you think of it as a sphere, it's a big O, just spherical atom, not atom, molecule. And if you think about it like this, north, south, east, west, we have an equal distribution of negative charge because all these bonds are exactly the same. So that gives us an overall blanket of negativity, which would be an equal distribution, which we would call nonpolar. Now, if you had, instead of carbon tetrachloride, let's say this was fluorine, and this was fluorine, would you consider this molecule to be polar or nonpolar? We were questioning this a little bit, right? So what you're trying to think of is, okay, can I get these chlorines and chlorines counter to each other so they can kind of cancel each other's dipoles? And can I get the fluorine and fluorine to cancel each other's dipoles? In a tetrahedral structure, what's the bond angle? 109.5. So there is no way for chlorine to chlorine to cancel out each other's dipoles or fluorine to fluorine to do it because there's no 180 angles. So because of that, this would be in the end Cl to F2. This would be a polar molecule because the dipoles would be different magnitudes, and it would leave us with a slightly unequal distribution of those partial negatives. Yeah.
So for the original chlorine tetrachloride.
Yeah, chlorine or carbon tetrachloride. Yeah.
So it has a dipole moment within it, but like overall it's still non-polar.
Yes. So that's what we're trying to see is you can have a dipole moment on a bond. A bond can be polar, like all those carbon tetrachloride bonds were polar, but because of the distribution of the charges that they have allowed, the molecule is nonpolar. Okay. So I think that's actually kind of what I have up here. So if the molecule exhibits an overall dipole moment, meaning the whole entire molecule has some unequal distribution of charge, it would be polar. But you do consider both factors. You consider the bonds and the molecular geometry to make your final call on that. And your visualization will help a lot with determining something's polar. It takes a hot second to get this down, okay? Everybody usually needs to work on visualization. Give me a thumbs up when you're done, okay? You're thinking, you're writing, or just looking forward. You have your left sheet out if you don't already. So this matters because what our next conversation will be about is intermolecular forces and how intermolecular forces cause certain properties like high boiling points, low melting points, volatility, solubility. So basically every physical property known to man will depend upon if the molecule is polar or nonpolar. So this is the premise of our success for the next couple weeks, is can you determine if something is polar or nonpolar? No pressure, okay? So that's why I'm going to basically make sure today you are the masters of polarity. All right, I'm going to go right past this, okay? So on our structure building today, First, you have to have a valid legal structure. Then you build it. I'm gonna come around and do your build. It's gonna take me a while. There's a lot of use of maybe 3 to 4 builds at a time. And then once you start running out of molecules, you can deconstruct. But I want to make sure you have you predicted the correct molecular and electron pair geometry, and then you can predict the right bond angles, and you can determine the polarity. So you'll do this for each structure. Cool? On the lab sheet, it didn't say electron pair geometry or molecular polarity. I'm adding that to the characteristics I want you to detail out for me, okay? And then if you don't know where that is on the lab sheet, it's the, towards the very bottom. Oh, I did make one change. Nobody says angular anymore. So say bent instead of angular. It's the same thing. It's an angle, like your bent elbow. So change that to bent whenever you start speaking in terms of bent. And then the RUs, the repulsive units, are only calculated on the expanded object questions. Okay? All right, so I would say work in pairs, grab a kit, disperse. Grab a kit, disperse. Work with a partner. I got 24 of you. A partner. Look at my picture. You don't have to allow me to stand up because you sit listening options. One of the most important parts for determining geometries is you have to find the central atom. The central atom is what you're counting ligands and lone pairs off of. You don't care about all the lone pairs in the entire molecule because they don't cause any disruption to shape. It's on the central atom. Got it? That is your main focus. Thank you. Keep this somewhat organized. I want to have these details. Organized. I just don't want to I don't know why I got We'll make these single bonds because they're just like longer and we'll make these double bonds. Wait, what?